In a one-dimensional finite element model, the math is straightforward. The bars connect in a single straight sequence, making it easy to assemble the stiffness matrix because every node follows the one before it. A two-dimensional truss structure is different. Its elements share multiple nodes and connect in a non-linear fashion at varying angles. These elements also possess different cross-sectional areas and are oriented at distinct angles relative to the global x and y axes. This creates a logistical challenge for the program, determining where to store the properties of each element within the final system equations. Without a fixed sequence, the algorithm needs a defined method to identify exactly which individual parts of an element's stiffness matrix belong in which specific slots of the global matrix. To manage this, we can develop a generalized algorithmic pipeline in MATLAB that handles these varying connections automatically. Solving the truss requires a powerful system that effectively maps physical connections into a unified set of linear algebraic equations. The first step in building the algorithm is to completely separate the physical drawing of the truss from the math. We divide the solver into two parts: the input data specific to the problem and the universal logic used to solve it. We bridge these two halves using registers, which act as data structures to store the physical properties of the structure. This decoupling ensures the solver logic remains the same regardless of the truss geometry, making the program applicable to any design. The program architecture is built on two primary structures: the node register and the element register. The node register defines each node's identity, coordinates, applied forces, and degrees of freedom. Each 2D node has 2 degrees of freedom: U along the x-axis, V along the y-axis. We initialize unknown support reaction forces as zeros to prevent interference with displacement calculations. The element register follows, linking each strut to its start and end nodes, while defining its material area and modulus of elasticity. Once the registers are populated, the solver handles the structural data as a purely numeric set, removing the need to reference the physical truss again. The program begins by pre-allocating an empty global stiffness matrix and an empty global force matrix. The size of this grid is 2n by 2n, where n is the total number of nodes in the system. The solver then enters the assembly loop, which systematically processes every single element in the register one by one. Within the loop, the program calculates the length of each element using the Pythagorean theorem and the coordinates provided in the node register. It then determines the sine and cosine parameters by dividing the change in x and y by the total length. This method uses the node positions directly to find the orientation, which prevents sign errors that often occur when calculating angles explicitly. The transformation matrix, T, converts stiffness properties from local to global coordinates. Multiplying local stiffness by T's transpose aligns properties with global axes. These values inject into slots in the 2n by 2n matrix. The solver identifies target slots referencing the node's degrees of freedom. If multiple elements share a node, the loop simply adds their stiffness contributions together in the overlapping matrix positions. This process translates a set of disconnected, angled components into a single comprehensive coordinate system. At this stage, the global stiffness matrix is singular, making it impossible to solve directly. Physically, this is because the truss is not yet anchored. Without constraints, the math allows it to move infinitely through space. To fix the structure in place, the program identifies the degrees of freedom at the support nodes that are prevented from moving. We enforce these constraints by removing the rows and columns associated with those fixed degrees of freedom. This smaller, dense block is the reduced stiffness matrix. The global force vector is reduced in the same way, leaving only the values corresponding to free movement. This reduction is the computational equivalent of bolting the truss to its supports, creating a system of equations that can now be solved. The reduced matrix can now be solved using standard matrix inversion or the backslash operator in MATLAB. This calculation provides the displacement values for every free node in the truss. During post-processing, the program reconstructs the full displacement vector by placing these results in their original positions and inserting zeros for the fixed positions. This yields a complete map of how every point on the truss deformed under the applied loads. While these displacements are essential, they are primarily used to calculate the internal forces acting within each element. The final step involves passing the full displacement vector back through a final loop.
By multiplying the transformation matrix and the local stiffness of an element against its specific nodal displacements, the program finds the axial force. This reveals the internal state of the structure, with negative values indicating compression and positive values indicating tension. This entire structural solver pipeline is completely modular. To solve a different truss with more nodes or different materials, the user only needs to update the data in the input registers. By organizing the matrix assembly through a systematic pipeline, the program can process any 2D structural system provided in the registers.